everybody, and today I'm excited to tell you about the new topic that I learned. It is about the usage of complex numbers in geometry. So you may ask yourself, how is that even possible? Like, how do they even have like a connection between them? But actually, it turns out there is a really tight bond between these two topics, and like solving geometry this way, I think, is way more interesting than the traditional way of like using angles and expressions. So yeah, let's get started. Firstly, what are complex numbers? So basically everything came out from this one statement, that I squared is equal to minus 1. We know that this so is quite literally impossible. Like the square root of minus 1 in normal algebra is impossible. But actually it turns out it is possible, and there's a whole new world behind it. So everything came from this one, and we'll be using the complex numbers plane to use it like in geometry and solve like real world geometry, like normal geometry. Yeah. Okay, so the basic thing is that z is equal to a plus bi, where z is our complex number, which we'll label as this, like as a c, two c's, and the I is our imaginary number, or in other words, like the complex number, and A and B are rational numbers. When we say we want to take the conjugate of a complex number, we mean this expression, A minus BI, where Z is our like complex number, and it has like this line above it. Okay, so this is the basic knowledge you should know. In the following parts, I'll show you how we can solve geometry without using any angles, without using um, like any trigonometry if you hate it, and we'll only use like these numbers and a lot of variables. Okay, so now let's talk about the properties of complex numbers. In this chapter we'll look at their perpendicularities and collinearities. So firstly we need to know the basic knowledge, and it is that if a complex number is equal to its conjugate form, then z is a rational number. How do we get that? Well, firstly, let's take a look at these two expressions. So we know that z is equal to a plus bi, and its conjugate version is equal to a minus bi. So if we make these both equal, make these two equal, we get that a plus bi equals a minus bi, where we can cancel out the a's and get that 2bi is equal to 0, or in other words, bi equals 0. Um, but from the beginning, we know that z is equal to a plus bi, but bi being 0 implies that it is actually the z equals a, where a is a rational number, so yeah, that's how we conclude that z is actually a rational number. Okay, and the second property is that if z plus its conjugate version is 0, then z is pure imaginary. What I mean by pure imaginary is that it can be represented by the product of a rational number and a complex number, as shown in the example below, where z equals r multiplied by I, where r stands for a rational number and I a complex one. Okay, let's move on. So here's the interesting part. You should really take a note. But firstly, we have to discuss one thing. So uh, let's take a look at a quadrilateral ABCD. And so in complex geometry, we'll only use the coordinates. We won't use like any sides, any lengths. So when we say A, B, C, D are complex numbers in complex geometry, then we mean the points A, B, C, D. So the point A will be represented as its lowercase version, the upper B will be a lowercase b, and so on, so on. So that's how we'll use them. For example, the midpoint of the line CD will equal C plus D divided by 2. Okay. So here it says that let A, B, C, D be complex numbers, and if AB, the line AB, is perpendicular to the line CD, then we get this expression. It is really important and really useful. It is used almost in every single solution, so you should really take a note of it. The second lemma says that if 3 points A, B, Z lie on one line, then it implies that Z minus A over Z minus B is equal to its conjugate form. Or in other words, we can say that Z minus A over Z minus B is rational, as we have proved here. And this is enough for us to know that ABZ lie on one line. Okay, let's get going. Okay, let's talk about the unit circle. So, it is a circle centered at point 0, having a radius of 1, and there's a property that for any point Z on the unit circle, Z conjugate equals 1 over Z. It is really important because if this expression takes place, then it means that Z lies on the unit circle. This is really helpful and is used in, I would say, every geometry problem that you could solve with complex numbers. And this is pretty much the basic knowledge that you'll need to prove other formulas, other statements. So let's move on to our first problem. Okay, so here's a new theorem. So it says that foot of the altitude from Z to the line AB is given by this formula. It may look really like frightening and like disgusting, but actually here's a really nice refinement of it. So if we have that points A, B, Z lie on the unit circle, then the altitude, like the foot of the altitude from Z to the line AB, let it be H. Then H is given by this formula: A plus B plus Z minus AB and Z conjugate. How did we get this? Well, firstly, let's consider this formula. So we have that A conjugate can be rewritten as A conjugate minus B conjugate multiplied by Z divided by 2 A conjugate minus B conjugate plus so we get that these two cancel out, and from here it gives us this formula: 1 over 2 we know that A and B lie on the unit circle. It gives us that A conjugate is 1 over A and B conjugate is 1 over B, just B. So this also gives us that and factoring everything, we get that it actually equals Z plus A plus B minus AB and Z conjugate. And yeah, simple as that. And this is really important. It's called the complex foot, I believe. And yeah, okay. So let's move on to our first problem. Complex Euler's line And as you may have known, it says that the centroid, the orthocenter, and the circumcenter are collinear, and now we're gonna prove it using only complex numbers. So how do we even do that? Well, firstly, we have to give some notations. So A, the coordinates of the circumcenter is 0, as it's the unit circle. So ABC lie on the unit circle. Okay. B, the centroid G, its coordinates are 1 over 3 A plus B plus C. I'm not gonna show you how I got that, because it can be really easily proven by using complex vectors, and it's not that hard. But the main issue here is that the orthocenter H, its coordinates are A plus B plus C. So firstly, let's show how we got this one. Okay. So to prove this, we use that the line AH is perpendicular to the line BC. By using the first lemma about perpendicularity, we have that 0 equals as A, B, C lie on the unit circle, we have that which, after equalizing this to 0, gives us that A, B, C, H conjugate minus AH equals BC minus A squared. If we do the same thing with the lines BH is perpendicular to CA, and CH is perpendicular to AB, we will get that if we take the difference between this one, I mean, we can do it with any, but let's do it with this second one and the first one. If we take their difference, we'll get that minus. Well, we'll get that. Well, as I've already stated before, A cannot equal B because their coordinates are not the same and they cannot be the same. So we can simply cancel these out, and that's how we get that H equals A plus B plus C. Okay, now that we've got that, how do we prove that H, O, and G are collinear? Well, by the second lemma, it is enough for us to show that G minus O over H minus O is rational. So if this takes place, then we have that these 3 points are collinear. But if we put their coordinates here, we get that G is 1 over 3 A plus B plus C minus 0, as O's coordinates, like the circumcenter's coordinates, are 0, and A plus B plus C minus 0, which equals 1 over 3, and obviously it's a rational number. So yeah, that's how we get that G, H, and O lie on one line. So this is a really easy version of the proof. Okay, now let's move on to some other problems. Okay, so here's a really interesting problem. So we have a quadrilateral ABCD and its inscribed circle, which is centered at point I, and N is the midpoint of BD, M is the midpoint of AC, and we need to prove that N, I, M are collinear. How do we solve this using only complex numbers, you'd say? But it's actually really quite easy, I'd say. So let's take a look at the lemma first. So this lemma says that if we have 2 points A, B, and tangents from them meet at some point, then that point's coordinates are gonna be 2ab over a plus b. Okay, now let's proceed to the problem. So firstly, let's only take the coordinates of these points. So z, w, x, and y. For now, let's forget about these points, a, b, and c, and let's define them using only w's, x, y, and z. So using this lemma, we get that a is equal to 2zw over z plus w over y plus z. Okay, now what? Well, knowing that m is the midpoint of AC, we get that m is equal to a plus c over 2. And applying a and c's meanings, values from here, we get that it actually equals we can do the same thing with n, which equals b plus d over 2, and it will give us well, we don't know it yet, but let I be the center of our unit circle, so its coordinates are gonna be 0, and let this inscribed circle be our unit circle. So to show that NIM is collinear, we have to prove that m minus 0 over n minus 0 is rational. Or in other words, m minus 0 over n minus 0 equals m minus 0 over n minus 0, its conjugate form. Well, we get, firstly we should know that m over n equals, well, after all of these things above, we get rid of them, we get that w plus x y plus z over z plus w and x plus y. Meanwhile, m over n conjugate form is equal to
what's a girl to do, lying on my bed staring.
So we should notice one very important thing, that actually m over n indeed equals m over n conjugate form. This implies that m over n is rational, which is enough for us to see that n, I, and m are collinear. As simple as that. A quite hard problem, that we solved using only complex numbers, complex bashing. So yeah, I think that's the end of the video. Thank y'all for watching it, devoting some time for this interesting topic, and I hope to see you in my new upcoming videos.